Okay, so in this video, we're going to talk about an error bound for alternating series. And what we mean by error bound here is, if you have an alternating series, for instance, that you know converges, right? So it sums up to some finite value as n goes to infinity. And you want to approximate this sum by just cutting off your series at some value of n. Let's say the 10th partial sum, for instance. Right? So let's actually work with this example. -1 to the n minus 1 divided by n squared. Right? These are the terms of your series. So, okay, so if you were to write down the terms of your series here, it would look like 1 over 1 squared minus 1 over 2 squared plus 1 over 3 squared, and so on. And so, okay, so it converges if you apply the alternating series test. Right? The magnitude of each term decreases as n goes to infinity, and each term also goes to 0. So if we just added the first 10 terms, right? So dot, 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 and then minus 1 over 10 squared, and we stop there. This is our 10th partial sum, right, for n equals 10. And, well, it's an approximation to whatever the value of this sum is when you add everything to infinity. And now the question that we want to ask here is, how good an approximation is this? Right, to the actual value, that is the sum. Now, think about those two conditions, right, that makes this series converge in the first place. So what are the two conditions again? So if b sub n is equal to whatever that positive part of each series is, then we know two things. That bn plus 1 is smaller than or equal to bn for all n, and bn approaches 0. Now the important thing here is this first property, right? Because if you drew your partial sums, right? Okay, so what do the partial sums look like? S1 would be just 1 over 1 squared, which is just 1. S2 would be the sum of the first two terms. That's 1 minus a fourth. That's 3 over 4. Right there. S3 would be 3 over 4 plus 1 over 9, so just slightly above 3 over 4. And you'll notice here that if you actually graph the partial sums for this alternating series, well, they're just going to go up and down and up and down, because every term you're alternating, subtracting, adding, subtracting, adding. That's your partial sums go up and down. Well, what does this help us in terms of using this partial sum as an approximation? Well, because of this first property here, that each term is getting smaller and smaller, well, this means that you can pretty much approximate where the actual value is, or where the actual sum of your series is, if you simply look at the next term. All right, so look at my drawing over here. First partial sum, for instance, or okay, let's start with something positive. Let's say their first partial sum is somewhere here. So you added a term, then you subtracted, now you're down here, then you added, then you subtracted, and so on. Well, if the terms you're adding and subtracting each time getting smaller and smaller, this is going to tell me that my actual sum is going to be somewhere in between these two values, right? Because, I mean, the magnitude in which you're adding and subtracting is only going to get smaller and smaller. So your sum must be somewhere in here. And so this is nice, right? I mean, if you look at like the actual graph here of negative 1 raised to n minus 1 over n squared. Okay, so again, these triangles down here, these are your terms of your sequence, right, or of your series. The red circles here are the partial sums. So I increase n. Next term here for n equals 4 is a negative, so it's going down for the next partial sum. Then n equals 5 goes up, and so on. Right, so the sums here alternate. So if I stop adding at n equals 10, this is the 10th partial sum, 0.81796. Well, what's the actual value of my sum? Well, I know it can't be farther away from 0.81796 than a sub 11, which is 0.00826, right? Because that's whatever you're adding to the next term, or to your partial sum. And again, by this argument over here, whatever your next term is, this actually gives you an error interval as to where the actual sum could be. So, okay, so for here we already said, okay, then it's actually B11, 1 over 11 squared. But let's actually state this formally. If you have an alternating series and you know it's convergent because of the alternating series test, right? So it satisfies Bn is decreasing sequence and Bn also goes to 0. Then it turns out that what we'll call the remainder term or the error term in your series, which is the exact sum minus the nth partial sum in absolute value, is bounded by, well, whatever this n plus first term is in magnitude. Right, and it's the b part of it, right? So it's only the positive part. So this is always positive. Right, and so for our picture here, for minus 1 to the n minus 1 over n squared, I can actually draw some interval around my partial sum. So this is now my second partial sum, right, as 2. And I know that A3, whatever it is, so it's positive, right? It's 1 over 9 here. That's going to give me an interval, right? Or a tolerance where I know the actual sum is going to be. Right? So I know my actual sum is going to be somewhere here because I'm adding this for the next term. And then every time I subtract or add after that, it's going to be smaller. If I add up to the third term, then now the fourth term gives me this error interval, and so on and so forth. Right? So if I actually tell you, well, the partial sum is somewhere here, I mean the actual sum is somewhere here, that's the red line, all these intervals actually will contain the red line. Right? So that's what we're saying. Since you're going up and down, but getting smaller and smaller, that red line denoting the exact sum is always going to be contained in this error interval determined by the next term in your sequence. Okay, so let's do an application of this where we're asked to pick n, right, so that we achieve some desired accuracy in our partial sum approximation. Right, so it's similar to when you were approximating intervals before, where, well, the larger n you pick, the closer you are to the actual value of your integral. It's the same idea here, right? The sum converges, right? The sequence of partial sums converge to finite value. So that means the larger you pick n, the closer you're going to be to that partial sum. I mean, to the exact sum. So what do we do in this case? So we know, and this is a different series here. It's only raised to the first power in the denominator. It's still convergent, right? So we know this converges by the alternating series test, since if you pick Bn to be just 1 over n, then it satisfies the two conditions we need. And this means that the error when we use S sub n to approximate the actual sum, it's going to be smaller than or equal to Bn plus 1, which is just 1 over n plus 1. So since we need this error to be at most 0.09, that means we're looking for n so that b sub n plus 1, which is 1 over n plus 1, smaller than or equal to 0.09. This means n plus 1 should be larger than or equal to 1 over 0.09, or n is larger than or equal to 1 over 0.09 minus 1. And so I'm looking for my calculator here so I can calculate this value. 1 over 0.09 minus 1. So that tells me that n must be at least 10.1111. Right? Because that's the value that will guarantee that Bn plus 1 is smaller than 0.09. Now, another way to do this is, I mean, you don't even have to solve for n in an inequality like this. Right? You can just keep plugging in n. Until we get some term to be smaller than or equal to the desired error. And so here you can do like 1 over 1, okay, that's 1. 1 over 2 is 0.5, 1 over 3, and so on. And then 1 over 10 is 0.1, not quite enough, but 1 over 11, okay, so what's 1 over 11? 0.09, 09 repeated. And so, what does this mean for us? It means, well, okay, so 1 over 11 is not actually less than 0.09. We need actually one more. 1 over 12, let me use my calculator here. 0.083. Okay, so this tells me that 1 over 12 must be my error term, which means I should pick n equals 11, which agrees with what we did over here. We need n to be at least 11 for that error to be smaller than or equal to 0.09. And okay, so let's view it here. Different series here, just n. Right, so if it's n equals 3, stop there. The error is 0.25. Because that's for n equals 4, that's a sub 4. N equals 4, it becomes 0.2. Right? 5, 6, 7. Just basically keep going here until, well, you see e sub 11 is finally smaller than 0.09 guaranteed, which means the 11th partial sum is going to work. Right? And this is actually like close to the actual sum here, this value.